So today I will start with the course logistics and then start talking about the basic differences between machine learning and federated learning. Okay, please feel free to use the chat anytime, so drop comments as we go. I will try to pick them up once in a while. Okay, so the quick overview of the course parameters. This is a 5-credit course, so this corresponds to approximately 130 hours of work. It's offered fully online, so there's no mandatory attendance. Some of you might be now in the lecture hall, so sometimes I will be also present in the lecture hall. And yeah, I encourage you to use this opportunity to come to the lecture hall and meet other students. But I understand that you also have busy calendars, so in principle there's no mandatory attendance for any activity. Okay, so the course roughly consists of two parts. The first part is the basic training camp, so to say. So in the first part, we have 8 lectures, which covers the main concepts, theoretical tools, and corresponding assignments, which test your understanding and familiarity with those tools. And this is the first part is, in a sense, the preparation for the main part, part 2, where you will work on a federated learning application in a student project. And in this project, we will also have peer review. You will hear more about the project later. So the focus now in February, March is on these lectures and assignments. Okay, so to be on the same page regarding skills or expectations, we will use some tools from linear algebra. So I expect that you are familiar with vectors and matrices and also have heard about norms. You will have time to review those concepts, but we will not provide an in-depth refresher in basic linear algebra concepts. We will use, to some degree, multivariable calculus. So if you know what a gradient is, this would make things easier. But again, you can refresh your memories as we go. There should be enough time for this. Yeah, we also assume basic knowledge of machine learning. So you should know what is empirical risk minimization, what is model training, what is model validation. And our assignments will require some Python coding. So basic familiarity with Python is also needed. Okay, I also want to point out this auto dictionary. So we have now also handed out to those of you who are in the lecture hall, we have handed out soft cover versions of this dictionary, which covers all the terms, most of the terms and concepts in depth. And also you will find in this dictionary links to or references to textbooks. So if you need to refresh your multivariable calculus skills, then you will find there good references for textbooks. Yeah, after completing this course, you should be able to represent federated learning applications using graphs. So you will also hear about graph theory a bit in this course as a nice mathematical tool to study and design federated learning systems. The core idea of this course, as you will see in the following lectures, will be to formulate federated learning as an optimization problem over graphs. So basic machine learning is an optimization problem in terms of empirical risk minimization, and in federated learning we extend this optimization setting a bit more by having optimization over graphs. Then you will learn how to design federated learning algorithms via simple, very basic distributed optimization methods. And you will be able to build and analyze or verify the trustworthiness of federated learning systems. So one important component of this course is also the legal aspects and ethical aspects of federated learning. So we will touch in the later lectures a bit the current regulatory frameworks like GDPR, data protection law, and the AI Act. Yeah, to put the course into perspective of other courses and curricula in particular, uh, the bare necessity courses should be matrix algebra. So these are example courses from Aalto University, and you might have had similar courses at your own or a different university. Uh, then we expect that you had a first course on machine learning, like a bachelor level course on machine learning, and some course where you used Python for data analysis. It's nice to have, but not strictly required to have a first course, have completed a first course in optimization. So we use only a very small set of optimization techniques. We will not use a lot of machinery. So you should also be fine if you didn't have a course on optimization first. But it can definitely not hurt. Yeah, and as follow-up courses, uh, I highly recommend, for example, the wireless systems course, because federated learning systems can be implemented over wireless communication networks. So in this course, we talk about mainly about mathematical models and algorithms, but at some point, these algorithms must be implemented in hardware, like in a smartphone. And then you might enjoy your knowledge from wireless systems, how to implement those federated learning algorithms in wireless networks. Okay, uh, about the schedule, as I said already before, we will have two parts, roughly two parts. February and March will cover the basics, the uh, absolute necessary tools that we then need for the student project in April and May. And we will have then a student kickoff lecture in the beginning of April. So you will hear more about the project and the peer review process in April. Overall, the idea is to use the student project to teach you or to give you an opportunity to exercise or to practice the preparation of scientific articles, like of a conference paper. And this also includes the peer review process. So this is like uh, a demo conference or a mock conference. You can view it like this. And I have had some cases of previous courses where these project reports were turned into actual conference paper submissions. Okay, so for the first part, we will have 8 lectures. The first one today, where we'll discuss how we transition from machine learning to federated learning. So we'll try to contrast machine learning with federated learning. The second lecture on Wednesday is about the main design principle. And then next week, we will have 2 lectures on federated learning algorithms, where we will show how to turn this design principle into practical algorithms. Then we will look at some special flavors or special aspects of federated learning. There will be 1 lecture on federated clustering, and this also contains some recent work. So some of the things you hear in this course is actually part of our current research in our research group. This also includes the lecture on explainable federated learning, where we will see how we can make federated learning systems transparent for different users, particularly for users who didn't have a course in machine learning or a master degree in machine learning. Then a very important aspect is the cybersecurity. We will look at some fundamental limits. How can we protect components of a federated learning system against adversaries? So somebody who, for example, injects manipulated data points or like fake news. how to avoid the spreading of fake news in a federated learning system. And the last lecture will discuss privacy protection methods. So federated learning is all about sharing information from your own data, but how can we do this in a way such that the privacy is protected to some degree? And we will see some cool techniques for this in the last lecture, lecture 8. Okay, then for each lecture, we will have one assignment. So there's one assignment per lecture, and the assignment roughly consists of small Python tasks, and also will test your conceptual understanding. So the grading or the assessment of the assignments is via quizzes, multiple choice quizzes, and these quizzes will be together with the assignment specification will be released right after the lecture, although you might have already seen this assignment specifications. So I can show here on the My Courses page, you find the link. Or actually, I can directly show we have a GitHub repository where these are shared, these assignment specifications. Assignments. And then you find here A1 PDF. So this is the specification for the first assignment, which relates to the lecture today. Yeah, so please carefully read this specification. And you don't have to submit anything. You don't have to submit the Python file. So you use whatever Python environment you want to solve these tasks or to implement the tasks that are described here. For example, here you have to read in data from a CSV file that we provide for you. And then you have to, for example, count the number of weather stations that are mentioned in this file. And then what we test is the results of this coding implementations, like the number of weather stations. And this we will test in a My Courses quiz. Or for those of you who are not auto students who follow the course as external participants, I will provide a Google Forms quiz and share with you the details soon. So the assignments are assessed via quizzes. You don't have to submit anything. In particular, you don't have to submit any Python code. Are there any questions at this point regarding the assignments? Please post them on the chat. No questions so far. So far, so good. Oh, here's one. Here they're coming. Do you grade assignments? Yes, so we evaluate the assignments via the multiple choice questions. So we don't care how you code it, what tool you use for coding, but you have to develop code to compute the quantities that we ask you to compute. Then another question is, do we have a Slack or Discord channel for course communications? No, I don't offer that. If one of the students is willing to organize a Slack or a Discord channel, I'm happy to distribute the link to the channel via our official announcements. But I will not. I'm not organizing a Slack or a Discord channel. You can use for the auto students. You can use the My Courses forum. There's a discussion forum on My Courses, or you can reach out to the course staff directly, to the team members. Yeah, and this remembers me actually that I forgot in the beginning. That was of course rude of me. I should introduce our team. So Let me now open this my courses page. So we have an excellent team of people who helped me with this course. First of all, Shamsiat Abdurrahmanova, currently a postdoc in my group, likewise Maza Asadi. Then we have Alexander uh, Pavliuk, Diana Pfau, Salma Rashidi, Salvatore Rastelli, Eckhard Schnorr und Mikko Sesto, who help with this course. And you will find here, so basically via their names, you know their email address. We have a pretty established format for email addresses at Alto, and you are welcome to reach out to them directly if you want, if you feel comfortable with reaching out to them by email. Otherwise, you can also use the My Courses discussion forum. So on the main page, there is a discussion forum and you can post questions there. Yeah, but as I said, if some of you is willing to organize another discussion forum like a Slack or a Discord channel, I'm happy to help you spreading the information about this discussion forum. Okay, no other questions at this point. Let me continue then. Yeah. As I said, you can use whatever Python environment you want or you prefer. For the Alto students, you can also use our Jupyter Hub. So if you don't have to install any Python on your computer, you can use a Python environment via your web browser. So it's pretty nice for Alto students. You can sign in with your Alto account that you also use for the My Courses login, and then you have your virtual computer with Python installed. Okay, yeah, then the quizzes the quizzes you have to answer, you will find on the My Courses page. What is important, you have only one single attempt, so there's only one shot, so to say, and in order to take your anxiety because you maybe some mess up one answer or you confuse something, don't worry about that. So you can book a review meeting at the end of the course where we can rectify any lost points uh, along the way. So this number of attempts is strict, only one, but in the end you can book a review meeting with me and we go through everything, and if you explain to me well why you answered the wrong why you answered choose the wrong answer here, then we can rectify the lost points. Okay, the assignment schedule is indicated here in these slides. Yeah, the slides, by the way, you also find on this GitHub repository under the folder slides. So this is the slide named Lecture Zero Course Logistics. So you find these slides also on the GitHub repository. And the first deadlines for the assignments is in 2 weeks. We give you 2 weeks for the first assignment, and then the same deadline is used for the second assignment. Yeah, there was a question about students from outside Aalto. So I have several hundred registrations from students outside Aalto who are interested in the course. And I cannot give you an official certificate, but I'm happy to provide you a confirmation letter, an informal confirmation letter. And I had cases in the last years where the students had a contact at their university which accepted my letter. So this depends on your local university. If your local university uh, is convinced by my letter, then it can be taken into account, I think. So this was for students from Swedish universities in particular. It worked for them. Okay, but as you are not enrolled at Aalto, I cannot give you credits at Aalto. That's beyond my power. Okay, but I can and I have provided course completion letters. So, what I'm going to say, the first deadline is in 2 weeks, Monday the 8th of March, and this deadline applies to the two first assignments. So please note that we have always one deadline for two assignments. So 1 week later, assignment 3 and assignment 4 is due on the 15th of March. 1 week later, assignment 5 and assignment 6 is due. So the idea is to give you some flexibility to schedule your work. On average, you have to submit on average, you have to complete one assignment per week. But we have scheduled the deadlines so that you have some flexibility in how you schedule your work in detail or precisely. Yeah, so the last deadline is end of March, on the 29th of March. Yeah, then, as I already mentioned, we have the second part, which consists of a project, and we will share more details at the kickoff event in the beginning of April. So for now, February and March is the hard time where you learn the basics. So to say, you learn the ropes, and then I want to see you applying the theoretical and algorithmic concepts to some project or in some application, federated learning application. And but what I want to point out now already is that we will have two rounds. So as now is customary in many scientific conferences, you have one review or revision possibility. So we have a first review in which ends in the beginning of May. On the 3rd of May, you have to complete your reviews. So each one of you has to review 3 to 5 reports of other students. And based on these reviews, you have to revise. You have to revise your report. So this should teach you this basic skill of leveraging feedback. That's a core skill in academia. How to make the most, first of all, how to give constructive feedback, and then how to receive or how to leverage feedback to improve your work. And then you have to show how you improved it in the second submission. The second submission deadline will be 7th of May, and the second submission will include the improved report and a response letter where you explain how you improved the report. And additionally, require you to submit a presentation video. Okay, so regarding the grading, the assignments will be used for the grading and the student project. But how in detail? So for the assignments, you can collect up to 40 points. So we have 8 assignments, 40 points, which makes 5 points per assignment, roughly. And 60 points can be earned, up to 60 points can be earned for the student project, where you will get, where you can earn points for the submission itself and for the review. So also your review performance will be evaluated. So don't think that you can just make blank reviews where you say excellent, excellent, or bad, bad, bad. You have to justify your reviews. If you don't justify them, then you might not get the full points for the review tasks. So in total, we have 100 points, of which 60 points come from the project and 40 points from the assignment. Yeah, I want to emphasize that there is no minimum requirement for any individual task. So you can have at some assignments 0 points, but in total you have more than 50 points. 50 points is needed for grade 1 to pass the course, and then we have regular intervals, always 10 points for the next grade. So for the top grade 5, you have to reach at least 90 points. 90 points. Yeah, as I said, don't worry if you are now for some reason mess up one attempt in this assignments or in the quiz. You have then a review meeting in the end where we can rectify lost points. very good comment or question. In somewhere it was indicated that the course is 5 to 10 credits. So I offer this 10 credit extension only reluctantly. So this will be up to negotiation with me when your performance is adequate. So I didn't fix the details yet, but I think you should achieve in the basic 5 credits variant at least a grade 4 to be eligible for this 10 credit extension. And the 10 credit extension would be something like I give you a small research task or a research question and you have to work on it. Or alternatively, you extend your student project into a full conference paper that competitive. Uh, so I must consider it competitive for the grading, of course, conference paper to get the 10 credits. Okay. Was there another question? No. Yeah, regarding the project workflow, again, we have two submissions. First submission is the first version of the project report, and you get feedback for those. In the second submission, you have to show how you used, or you have to explicitly explain how you use the feedback from the first round to improve the report. And in the second submission, you also have to include a recorded slide talk. Yeah, for the first submission, we fixed the data set because there was some challenge in last course editions that students were stressed because they didn't know what a good data set is. So we will take this anxiety away and fix the raw data set. But otherwise, you have full freedom. Yeah, I will skip this now for the sake of time because, as I said, we will have a project kickoff event anyway, and today already the minutes are running quickly. So you can also look up these details in the slides if you wish, but for the moment it's not that relevant. So we will have on the beginning of April a lecture dedicated to the project. Okay, yeah, before I now start with the actual content, the two ground rules that are very important for me. And these are basically two simple rules that are the quintessence or the essence of the Aalto University Code of Conduct, which I also want to point out here. For those of you who didn't read it yet, might be interesting read. And the most important thing for me is to have a safe learning environment. So I'm a very generous, very friendly person by nature, but my attitude can change abruptly when I see disrespectful behavior. So I don't want to see any disrespectful conduct, comments on anywhere regarding to the course or in general. I don't tolerate this. In particular, not in my course. So be respectful to others and also be honest. So that's a key requirement for, in particular, when you work a lot independently or as a researcher, uh, but also as student. Do not use the work of others without giving credit. That's the basic rule. So be honest about your own contributions. And in particular, if I get the idea or have a suspicion that somebody uses others' work or cheats in a sense, uh, then this will be handled rigorously. So we have a dedicated coordinator for such academic misconduct cases, and I will not hesitate to contact those people. So simple rule, just be honest. Don't use others' work or somebody else's work without giving credit. For example, don't just use the results that somebody else gets for the coding assignment and use them to fill out your quizzes. So we have some measures in place to detect such cases. Don't do it. Yeah, and then the second rule, what I already pointed out, be respectful. There is no tolerance for any kind of bullying or disrespectful behavior. Okay, any questions at this point regarding the course logistics? Okay, then, yeah, here's a question. The question is, can we submit the revised report or project work after the course completion in any standard conference? Yeah, I mean, you can do with your work whatever you want. Sure. Yeah, the question, how can non-Alto students submit assignments? And as I said, I will set up, instead of this My Courses quiz, I will use Google Forms quizzes. So we just use a Google Forms to test your assignments. And for this project, I'm still pondering what the best way is. Last year, I used a conference management tool like this ERDS, no, EDAS. But I'm not sure if I might try to. I actually would like to learn what's the bare bones way to implement a peer reviewing event. Maybe we will also use Google Forms for this. Okay, but I don't know yet how to implement this project submission for the non-Alto students. The Alto students will submit their project reports via My Courses. Okay, so let's now start talking about federated learning. In particular, let's contrast federated learning with machine learning. I guess some of you have taken this or took this course because they thought it's a nice follow-up for machine learning. But what's now the difference between federated learning and machine learning? So to give you two slides reminder of machine learning is about learning a function or hypothesis map that reads in the features of a data point, like the features could be the username, the mood, daytime, and then it outputs a prediction for something. The prediction here could be what is the best song or which song would this user enjoy most now? So far, so good. And how is it done? Well, we learn how to predict from doing it and making errors. So you learn this hypothesis map h of x by trying to minimize the errors or prediction errors on a training set. And you can also do this online. So as a new data point comes in, you get a new prediction error, and you adapt the hypothesis a bit. So how is it done in Python? This is now like a piece of cake nowadays with all these high-level programming languages. And now, additionally, now you have large language models who help you to translate your needs or your wish for the program or for the machine learning Python code into code. So you almost don't need to learn any coding anymore because you ask some LLM to spit out a small chunk of Python code that reads in data and chooses a model, trains the model, and then computes the training error and validation error. So far, so good. And then, I mean, then it's not over. That would be too easy to be good as a machine learning engineer. Is you have to do more because then you have to diagnose the machine learning method. You have to compare the validation error against the training error to detect overfitting. And if you have a baseline or a fundamental limit, that's what I'm always eager to know. Is there a fundamental limit? Do you know what the ultimate smallest possible error is? Because if you know such a baseline and you see that the training error is close to this baseline, and ideally also the validation error, then you are done. So that's the goal of machine learning engineering. You want to find a model such that the training and validation error is on the same level as the baseline or the accepted error level. And the hard life of a machine learning engineer is about getting there. So if you see the validation error is too large, what could you do? Or what could this mean? Like in this picture, if the validation error here is much larger than the training error, what could that mean? So this could hint at overfitting. And how can we combat overfitting? Well, you could use smaller models or larger training sets. And this is one way to improve or to develop machine learning methods. Another more convenient way, which is also at the core of how we approach federated learning in this course, is regularization. So instead of actively collecting more data points, you say the data points, they are characterized by features which are measured by sensors. And sensors have errors, intrinsic errors. So instead of this blue original data point, I could have almost equally likely observed this red one, a slightly perturbed one. And then you can say I could also have almost equally likely observed this left one. So you can augment each original, or you can augment the original data set by many small perturbations, and this way you increase the data set, or you enlarge the data set. And it turns out when you then look at the training objective function, or this empirical risk, this adding perturbations is actually the same as adding a penalty term. So some of you might have heard about ridge regression. Ridge regression is about adding a penalty term to the training error of linear least squares regression. But you can show that this adding the penalty term is equivalent to adding many perturbations, particular infinitely many, which are drawn from a probability distribution. And then also this adding a penalty term, on the other hand, has another nice interpretation as a Lagrangian. So some of you have heard about optimization or constraint optimization problems. So in constraint optimization problems, it's always nice to get rid of the constraints. And here a constraint could be that the hypothesis map cannot be too steep. So you prohibit too steep hypothesis maps. Or you constrain, this can be translated into constraining the model parameters. So the norm of the model parameters must be smaller than 1. And such a constraint can be enforced by adding a penalty term. So it turns out that regularization can always come in 3 different forms. Either data augmentation, or adding a penalty term to the loss function, or constraining the model, changing the model. And in some applications, one of those is more convenient. So adding a penalty term to your loss function requires you to have access to the loss function, like in scikit-learn. So maybe some of you know this Python library scikit-learn. It's not always so easy to manipulate the loss function. This is, on the other hand, it's very easy when you use PyTorch, as I understand. So I'm not an expert in PyTorch, but as I have seen in PyTorch, you have pretty neat ways to modify the loss function and to add a penalty term. This is not so easy in scikit-learn using decision trees, for example. But what is easy in scikit-learn or any machine learning framework typically is to add data points, artificially add data points. So instead of manipulating the loss function, which you could do in PyTorch, you could also just augment the data set, for which you don't need to have access to the loss function. Okay, any questions at this point? This was really quick, 5 minutes recap of machine learning and regularization. But yeah, I want to already point this out. This will be the key tool to couple machine learning machines or machine learning devices in a network. We will use regularization between devices. So let's say I have one device and you have another device, and we use my results to regularize your training. And that's how we couple individual machine learning instances and get a federated learning system. Yeah, that's the idea behind our approach. So in this course, how we approach federated learning. In federated learning, we train several models. So each, let's show, where do I have this here? Yeah, let's say we have instead of one data set, like here in machine learning, left part of the figure illustrates machine learning. We have one single data set, like on your computer. And on the right side, we see a federated learning system, which consists of many different data sets or local data sets. And in federated learning, we in principle train a separate model for each of these local data sets. And these local data sets could be patients, could be the data collected about a patient. And we want to train for each patient a personalized diagnosis method or a healthcare assistant. But how do we couple those? How do we couple those individual machine learning uh, instances? And the idea is we use the behavior or the predictions of one model as like virtual labels for the training at another data set. So we use the predictions that we get from this green model on a test set. So we need to agree on a test set, which can be completely artificial. We use the predictions of this green model on this test set as for the augmentation of this data set here for training the blue model. That's the core idea. That's how we couple the training of these individual machine learning models. We use the prediction of a single model to augment the data set at another for the training of another model. Yeah, and this in Python, this can look very, very simple. So it can look very almost trivial. So if I look here at the machine learning implementation in Python, we read in data, we define a model, and we train the model. So what is the difference then in federated learning? In federated learning, we have several devices. So these devices must communicate somehow with each other. So let's say they have an IP address. Let's assume we have for each device an IP address, and we can send and receive data from another device by using their IP address. And we can then use these communication links to obtain the predictions of this model here with the IP address 192.168.0.2 to augment the data set at the device with IP address 0.1. So the difference between machine learning and federated learning is that we use predictions from other clients to augment our own data set. And that's how we couple these individual machine learning instances. And one extreme case is each device, like my smartphone, runs one machine learning method, is one machine learning instance. And we now can couple them over the network. Okay, any questions so far? This question, in the example you have given, aren't we sharing X? Yeah, so you need to the nodes need to agree on a test set. Yes, so the nodes need to agree on a public test set, or uh, this would require a centralized server who maintains this test set and informs every participant about this test set, or we will see methods that can have a different test set for each pair of nodes. So think about a peer-to-peer network. So you just discover, for example, I roam around with my smartphone and I come across another smartphone in a Bluetooth range. So these two smartphones can now agree. There's a simple protocol which discovers the other. Let's say they are both running a federated learning app, general purpose federated learning app, and they agree, I found you, let's collaborate. So we agree on a test set. And this test set could be generated by random numbers. So next question. How individual inductive biases of each machine learning model is taken care of. Yeah, so the individual models, they must be useful for the individual learning task, but the local data set is too small. So we assume that somehow we know what a good model is. So this is not really covered in our course to find the right model. We assume somebody has said, okay, I want to use a decision tree, but I have too few data points to train a deep decision tree, so I need to collaborate. Next question, you mean there is one base model? Uh, no, so in this case, each device with a separate IP address has its own model, its own, we call it local or tailored model or personalized. This could be my smartphone here. I have my own model. I use a SGD regressor. This uses one specific model. Then there is another, my friend has another smartphone with this IP address and uses a linear regression model. And yet another friend has this IP address and uses a decision tree. So the methods that we will teach you in this course, they allow for each node or each device has a different model. There is no single global model. We will see that there's a special case where all devices learn the same model. So this is also known as this is similar or equivalent to a server-based federated learning. But we see this as one special case. Often you hear federated learning uses a server, but it's not necessary. You can do federated learning in a peer-to-peer network without any server. But also in this peer-to-peer network, you could, if you want, you can use the same model or same type of model at each device, and we will see how to ensure that the coupling between these devices is so strong that all devices end up with the same model. But in some applications, it might not be useful. In some application, it might be useful that you allow for different models. Let's say for personal fitness assistance. So I shouldn't get the same recommendations as an as who is now at the Olympic Games, this Johann Klöbö, this superstar cross-country skier. I should not get the same recommendation for a fitness plan than he, because then I would die. So I should have a different model. Next question. Doesn't taking the predictions from another node taint the data in some way? Very good point. Very good point. So one key challenge is to find out with whom should you collaborate. So we will see how to analyze the behavior of this federated learning system when you fix the collaboration pattern, or you fix which nodes collaborate with each other. But it turns out when have very different data sets, like me and Johann Glöber, we should not collaborate. We are too far away, so to say. But we will see, or I will briefly discuss those in one of the lectures, methods to find out if you should collaborate. I mean, I pointed out already here, do you know some basic methods to find out if you should collaborate with somebody else in training a model when you know some basic characteristics of your data sets? Are there principled ways to find this out? So let's say I or let's look at this. Where do we have it? This data clouds here. So let's say I have this data cloud, and then I come across somebody else which has that data sample. Are there principled ways to find out if they could come from a similar distribution? Yes, computing some statistics or tests. Did any one of you hear about, I guess it's called t-test? Isn't there something called t-test, which is about finding out if two samples, like this sample here and this sample, come from the same distribution. So there are some, and this is old knowledge. So this is, I think, hundreds of years old. So there is some hope to find out who to collaborate with. But I must say it will not be the focus of this course. So in this course, we mainly assume that this collaboration patterns is given. Yeah, next question. So for example, the predictions of another machine become ground truths or target in the local machine. Yes, that's the idea. So the idea is in this augmentation picture, so these blue data points would be my own data points, and the red ones are obtained by using as label the predictions obtained from another device. Yeah, that's the idea. Next question. How do you define from multiple devices which one to augment the data with, or does it simultaneously augment with all the nodes, or do we use, for example, three devices and then augment one? Or based on what criteria do you choose which single one to augment the data with? Yeah, that's what I just discussed. This is a hard question to find out which other device to collaborate, but there is some recent work. I'm happy to share this then also in the chat. So find your friends in federated learning. Let's see if you can you see my screen share? Yeah, federated learning can find, so there's an active line of recent research. So this was from 24. Federated learning can find friends that are advantageous. Okay. So there is some, and as I have seen in the basic idea is similar to the t-test. So you compute some statistics. So let's say you compute the mean and the variance of these data sets, which do not reveal too much privacy, and then compare them. And if they are too different, then you say, I don't collaborate. So you use statistics, basic statistics. Could be one way to find out who to collaborate with. Very good question. Next question. What does it mean by augmenting data? Do we replace the true labels of the test set with the prediction from the other device? Yes, that's exactly the idea. Yes. Next questions. Is it possible that devices, IP addresses, are in a different subnet and the communication still take place? This depends on the network architecture. So we don't go into this implementation details. This then is a question of how you implement this federated learning system in practice. This is a networking question. This is beyond the scope of this course. Next comment or question, are we kind of averaging the weights of different models to arrive at the central model rates? Yes, exactly. That's one effect. So we don't do this directly here because we just augment. But if you augment a lot of data points from your neighbors, then in the end, you will see this in our lectures. The effect is that the federated learning algorithm ends up averaging the model parameters. But I want to highlight that this idea here is this data augmentation idea doesn't require model parameters. So this idea of augmenting your local data set using predictions from your neighbor, you can do with any model that delivers predictions with decision trees. So there are no model parameters, but you can also use it for parametric models. And for parametric models, it ends up as averaging, being like averaging of the model parameters. Next question, using clustering algorithms. Yeah, I guess this is related to the question of to find out which nodes or which devices should collaborate with each other. You can also use some clustering, yes. But you would need to do it in a privacy-friendly way. So this is of course not trivial, how to cluster the devices to find out who should collaborate with each other. Uh, Next comments, yeah, please don't call me sir, just call me Alex. Uh, if it's okay for you. Federated learning is said to preserve privacy, but it leads to slower training and higher infrastructure cost. In practical systems, how do organizations justify this trade-off? I don't know. That's a tough question. I hope to teach you some mathematical tools or techniques to research this. to actively research this. So one of my dreams is that we find out how to develop a federated learning system using our smartphones in a very decentralized, democratic way to have something as powerful as an AI compute factory that we, or I think nobody here in this Zoom meeting can afford to build an AI super factory. Even countries cannot do it. Only some very rich, typically US people can do it. But can we? We have in Europe 700 million, roughly, no, 500 million people, most of them with at least one, maybe some of them with three smartphones. How can we couple the computational uh, capability of these 500 million smartphone devices to be as powerful as the supercompute centers of OpenAI? So I don't know yet. But this would be an interesting research question for the 10 credit extension. If you're interested in exploring this seriously, we can have a talk towards the end of the course. Next question. A comment. Are there links between federated learning and ensemble learning? That is combination of predictions from several models to obtain an increase in performance. Interesting link. I didn't think about this link yet, but it sounds intuitive. I'm not that familiar with ensemble learning techniques, but yeah, I need to think about this and give you a more useful answer, more principled answer on this. Interesting link. Yeah. Okay, I really like the activity here. We have still a few minutes to go. Yeah, please continue posting your comments or questions. I will now continue with, I will skip these applications or just mention this briefly, federated learning applications. One application that I like and that we will also use a lot in the assignments and in the project is weather forecasting. So we could think of the weather stations installed in Finland as these devices. So each weather station could have one small computer or device with an IP address, and we want them to collaborate efficiently to get better weather forecasts. So this is a nice example for a federated learning application. And another application would be Finnish road safety, where you can nowadays you can use your LLM to provide you a Python script that reads in the current snapshots from the road cameras. And you could then train a separate model for each road camera or for each road safety station to optimally predict the risk of ice based on the webcam snapshots. Yes. Okay, so a real-world federated learning system can be very complicated. A lot of different devices. Maybe some of you have already smart homes, and in some of these smart homes, already the light bulbs are smart. So you can buy in your favorite consumer electronics shop, at least in Austria and in Finland, I have seen light bulbs with some intelligence. These light bulbs could be devices within a federated learning system. You can also include in this federated learning system a bit more powerful light bulb, which is this Lumi supercomputer in Finland. So in principle, a federated learning system can be very heterogeneous. You can have very different types of devices, very different forms of connectivity. So you might have high-speed fiber cables connecting devices. You might have low reliability wireless connections somewhere in the ass of nowhere in Austria mountains. Very different conditions, very different computational capacity. So this might run out of battery all the time. Some devices join or leave. So it's a very complicated system. So in order to bring in some order into the system and to reason about a federated learning system, to make some inferences or reason about it in general, we need to kick out a lot of details. We need to abstract away a lot of system details. And one such abstraction that will be used heavily in this course is the concept of or the notion of a federated learning network. So a federated learning network is something like a graph, an undirected graph. So it has nodes. Each node represents a device like a smartphone, and the edges represent collaborations. So if two nodes are connected by an edge, this means they collaborate in some way. And this typically requires a connectivity. So there should be a wireless link or a fiber, optical fiber cable between them. And this amount of collaboration we quantify by an edge weight. So we assign to each edge an edge weight, a positive number. Yeah, so how many of you have heard about graphs in some course? Raise your hands or post something on the chat. Yes, so some of you have heard about graphs. So what is now the difference between just a graph and a federated learning network? Well, in a federated learning network, we have something sitting on top of the nodes. At each node sits a machine learning task. And this task is characterized by a data set or a data source, a model that we want to train, a machine learning model, and a loss function. So if you are a mathematics connoisseur or aficionado, you could think of a federated learning network as a function defined on the nodes of an undirected graph. And the values, the function values are tuples of dataset, model, and loss function assigned to each node. Okay, I want to just highlight that this is a big approximation or a crude approximation. We kick out a lot of details, so we will have a modeling error since we cannot take into account all the nitty-gritty details of an actual federated learning system. But the hope is that the simplified model, abstract model, allows us to do more reasoning or to predict something about the behavior of a federated learning system, like will it learn useful predictions. Okay, yeah, here you will use some Python code in the assignments to build a federated learning network. So for this, I warmly recommend and I encourage you to use NetworkX. So NetworkX is a Python library that allows to work with undirected graphs or networks. And what is really cool about this NetworkX is, in my opinion, you can attach to the nodes attributes. And these attributes can be almost anything, any Python object. In particular, you could say the node 1 has attribute called model, and this model is a linear regression object. So you can attach really to each node a machine learning object or a model, like this linear regression. And to another model, you attach another machine learning object, like a decision tree. So this is pretty nice in Python. And you can also represent the edges nicely. So you can add edges conveniently, and you can also assign weights to the edges. Okay, and yeah, just to remember or highlight, in principle, you can have different models at different nodes. So one node or one device uses a linear regression model or a linear model, and another node uses a decision tree. And still you can do something with, they can collaborate somehow because they only exchange predictions on a test set. And this can be compared between a linear model and a decision tree. But you don't have a parameter vector here. So much of current federated learning literature assumes you have at each node a model parameter W, often symbol W, and you then average the model parameters. But you cannot do this if one node uses a decision tree. But the methods you learn here in this course, they allow to have very different types of models at different devices. Okay, so we have a model at each device. Each device wants to train a model, or in other words, wants to learn a useful hypothesis map out of this model. Remember, a model is a hypothesis space. Yeah, I want to repeat again. Whenever you're unsure about the meaning of a word or terminology, please look it up in our dictionary. That's very, very convenient now that we have this dictionary because anytime you struggle with a term, just look it up in our dictionary. Or, if necessary, please reach out to us by email. Yeah, beside the model, we need a loss function. Otherwise, we don't know if a model is trained good or not. So we need a loss function. And also here, we can have different loss functions at different nodes. So some nodes might use a squared error loss, and another node might use a clustering error, might run a clustering method. Still, we can couple them via predictions on a test set. Yeah, here's the example when we use as a local model a linear model and the squared error loss. So then we can write down the local loss function as a function of the model parameters. And it looks like this. So the local loss function is the average squared error loss on a local data set or local training set. But there might be other nodes which must somehow estimate the loss from a reward signal, like in reinforcement learning. So you could also couple reinforcement learning devices or devices which run reinforcement learning with other devices who do clustering, and the third device does linear regression. Okay, so that was about the nodes and the loss function and model assigned to the nodes. So what about the edges? So this federated learning network consists of undirected and weighted edges. And an edge means, the presence of an edge means the two nodes that are connected by the edge, they collaborate. They augment their data set with the predictions of the other side of the edge. And for most of this course, we assume somebody tells us. Somebody prescribes this edge set. But in practice, it's good to use data-driven methods to decide where to put an edge. But this is a bit beyond the scope of this course. Okay, and yeah, the role of an edge is also implementation wise, we need to communicate. So an edge means we couple the training of the local models, but also we need to communicate between those two nodes. So it doesn't make sense to use a federated learning network with an edge between two nodes for which it is very hard to implement a communication, to implement direct communication link. So if there's no possibility to communicate between this node and this node, then maybe we shouldn't use an edge in the federated learning network. So this is also a design choice, if or a modeling choice. Okay, so a bit of terminology that will be useful in the course. We call a federated learning network uh, connected, or the graph of a federated learning network. Yeah, I will be a bit sloppy in the course. So I sometimes say the graph of a federated learning network, but sometimes I mean by the graph G actually the federated learning network itself. But the difference between the graph and the federated learning network is that in the federated learning network, each node has something on top of it, has a model and a loss function. But regarding the graph itself, we call it connected if there is a path between any two nodes. A component is a connected subgraph where there are no edges between those two. Then we will use the notion of a neighborhood of a node, which is all the nodes that are connected to it. And sometimes we use the weighted node degree, which tells what's the total strength of the outgoing links of a node. So we add the edge weights. So this is different from the plain node degree, which just counts the number of neighbors. We also take into account the edge weight here. So that's why it's called weighted node degree. And then the maximum node degree is, as the name suggests, the maximum over all weighted node degrees in the federated learning network. Okay, here's an example of a federated learning network that consists of 6 nodes. Each node represents a device. And this federated learning network has two components, two connected components, C1 and C2. There's no edge between those two. Um, the edge weights are assumed all equal to 1, so that's a good first modeling assumption. If you don't know that some collaborations are more intense than others, then start with assuming all are equally intense. So all edge weights are equal to 1. Then we have two components here. The first component is 1, 2, 3, and the second component consists of nodes 4, 5, 6. Yeah, then the node degree or the weighted node degree of node 1 is 1 because it has one neighbor. The weighted node degree of node 2 is 2. It has two neighbors, 1 and node 3. Okay, so I just want to now point out then the difference between a federated learning network and a federated learning system. So a federated learning network is something static. There is no time evolution yet. So in a federated learning system, we run algorithms on top of the federated learning network. Next week will be dedicated. We will have two lectures next week dedicated to algorithms, and these algorithms they send messages across the edges. So a federated learning algorithm is in a sense a specification of when and how model parameters or predictions on a test set are shared between connected nodes. So in a federated learning system, we have also a dynamic component. Something happens over time. A federated learning network is something static. It's a static description or model of a federated learning system. Okay, just to tell a bit more about these algorithms. So a federated learning algorithm in this course means the application or the repeated application of update operators. So each node uses the current model parameters. So let's stick to, for the sake of exposition, let's stick to parametric models. But most of what we tell about can be easily extended to any type of model, also non-parametric models. But let's say we have parametric models at each node. So each device maintains a model parameter. So a federated learning algorithm consists of the repeated application of update operators that I call here calligraphic F superscript I. So here each node has its own operator, its own update operator, because each node has its own local data set and a potentially different model. So the learning progress is different, or the learning evolution is different at each node. And we capture this by having different update operators at different nodes. Okay, now regarding the network structure or the graph structure, it's often useful to have a few numbers that characterize the graph structure or the connectivity. And one way to get such a few parameters that characterize a graph structure is via matrices. So maybe some of you had a course on graph theory, and one big theme in graph theory is spectral graph theory. And spectral graph theory uses matrices to describe graphs or networks. And one such matrix is the Laplacian matrix that we will use a lot in this course, which is defined by putting the edge weight, the negative value of the edge weight, whenever there's an edge between node I and I prime. And the main diagonal entries are the weighted node degrees for each node. So for the ith main diagonal entry is the weighted node degree of node I. I've shown here a small example to illustrate Laplacian matrix. So we have a federated learning network with three nodes. And on the right, you see the Laplacian matrix here. So node 1 corresponds to row 1 and column 1, has a weighted node degree 2. It has two neighbors, 2 and 3. So the entry here is 2. Then between node 1 and node 2, column 2 is an edge with weight 1. So here's -1. Similar for row 1 and column 3 is -1 because there is an edge between node 1 and node 3. So each node here corresponds to one row or one column, and the edges correspond to an intersection between a row and a column. Okay, and it turns out that the Laplacian matrix has several nice properties. For example, it's symmetric for an undirected graph. This is more or less direct consequence of the undirectedness, and it's positive semi-definite. So when you compute this quadratic form, you obtain this expression, or you can show that this quadratic form is given by this expression, and this expression is clearly always non-negative because these edge weights are positive, non-negative, and the square here, the square of the differences is also non-negative. So the whole thing, the sum of non-negative numbers, is non-negative. So this whole thing here is always non-negative, and this means this is a positive semi-definite matrix. And the nice thing, maybe the nicest thing about positive semi-definite matrices is they allow for a beautiful decomposition, which is called the spectral decomposition. So you can write a Laplacian matrix as a sum of rank 1 matrices. So each rank 1 matrices is the outer product of an eigenvector. So these u vectors here are eigenvectors, and they turn out to be, you can choose them orthonormal, as orthonormal. And the scaling factor for this rank 1 matrices are the eigenvalues. And these eigenvalues, they are non-negative and they can be ordered starting from 0. You can show that 0 is always an eigenvalue of a Laplacian matrix, which also means that it's non-invertible. It's singular matrix. And they are upper bounded by 2 times the maximum node degree. So why this hassle of bringing in the matrix and this eigenvalues? Because you can use these eigenvalues, in particular the eigenvalue lambda 2, this second smallest eigenvalue, to find out if a federated learning network is connected. So one way to test if a graph is connected, look at the second smallest eigenvalue, and if it's 0, then it's not connected. What is more, you can show that, or one can show that the number of 0 eigenvalues, so the number of components here in the spectral decomposition, which have the 0 factor here, or 0 value, a scaling factor, is the number of components. So if you would have 3 components, then you would have the first 3 eigenvalues here in the sequence are equal to 0. So the test if a network is connected amounts to computing the eigenvalue decomposition of the Laplacian matrix. And if the Laplacian matrix only has one 0 eigenvalue, this lambda 1, then you know it's connected. Whenever this Laplacian matrix has more than one 0 eigenvalue, then you know it's not connected. Okay, so let's wrap up this lecture with an overview of some federated learning flavors. As I mentioned already, in the literature, often federated learning involves a server. So when you read a federated learning paper, at some stage in the introduction or problem setting, there comes a server. A server is mentioned. But this is only a special case. So we will see in the later lectures that this server-based federated learning is just a special case of a fully distributed way of doing federated learning. You could just randomly pick one of the devices, let's say my device, and say this is now the server. And then obtain the server-based or can imitate any server-based federated learning system. So, but de facto, there's nothing special about having one node as server. You can also do federated learning in a more decentralized or democratic way. You don't need a server for this. Okay, then horizontal federated learning is one main flavor where each device carries data points that belong to one underlying big data set or main data set. And this local data sets or the data sets at the devices, they can be overlapping. What could be an example? Let's say some weather stations Some weather stations also carry or store the weather measurements at neighboring weather stations. So some of these local data sets, they are overlapping. But there can also be no overlap. So this is then the most direct form of federated learning. So each device has some data points which have the same structure. So the data points are characterized by the same number of features and the label, but they represent different data points. Fundamentally different federated learning flavor is called federated learning. In federated learning, the devices or the components of this federated learning system, they all store information about the same data points. So all devices use data from the same data source or use the same data points, but the devices have different features, so that each device uses a different set of features. So does any one of you have an example for vertical federated learning in the context of public administration? Let's say in Finland. Let's say in Finland, where each data point is a person. So one data point is me, another data point is my friend, and the last data point is my doctor, let's say. So which institutions could be devices in a vertical federated learning setting? So who carries different features about the same persons? Let's say the population or the underlying set of data points are all Finnish citizens, or now let's say then this would exclude me. Let's say everybody with a Finnish social insurance number or a Kela card. Can you think of different institutions? Yeah, very good. There are examples. One could be Kela. Another institution could be the police, which hopefully doesn't have any particular features about me. A third institution could be S-Market, where I have a shop card, customer card, so they know some features of me, how much meat I bought last week, but they might not know the latest healthcare records from Terveystalo. So there could be also Terveystalo. So all these different institutions have data about, in principle, about the same population, people living and working in Finland. But each institution has a different view of the data points. So one institution is the bank, who sees the financial transactions. Another institution is the police, which sees if somebody behaved badly. And they could be combined, of course. For some reasons, it might be useful to combine those. Let's say when there's a police investigation or something, an anti-terror mission, but it must be in a controlled way. And federated learning, to some degree, allows to combine this information from different institutions in a privacy-friendly way. I don't say privacy preserving way because there's always a bit of privacy leakage. So I call it privacy friendly. It's often the question, how much privacy leakage are you willing to tolerate? And you will see in a later lecture how to measure, how to come up with quantitative measures for privacy leakage. Okay, I might skip this for the sake of not torturing you too much today. It's quite long already. So to conclude, before I take some last questions, so basic machine learning is to train a single machine learning model from a single data set. For example, in your own laptop or your own smartphone using Python's scikit-learn. Federated learning now means we have several devices, which could be some laptops, smartphones, wearables, light bulbs. So a federated learning system consists of typically very different types of devices. And each of these devices collects its own data set. I don't know what a light bulb collects, but my smartphone has fitness tracker apps, so they collect my movements. And each device trains a local model. And we obtain different flavors of federated learning by using different forms of collaboration between these devices. So the most fundamental way to collaborate is to share predictions on a test set. So two devices come across each other, they agree on a test set, which could be subsets of their own data sets, and then they exchange predictions on this common test set to augment each other's data sets. Okay, so in the next lecture, which in some way will be the core lecture, the conceptual core lecture of the whole course, we'll introduce a design principle for federated learning, which is called generalized total variation minimization. And the idea is to formulate this federated learning or this coupled training of models as an optimization problem. Similar as we formulate basic machine learning as empirical risk minimization, we will now use GTV minimization as the basic formulation of federated learning. And once you have formulated federated learning as GTV min, we extract from this designs for algorithms. So we will see then in the following lectures how very naturally or almost trivially you can extract algorithms from this GTV min problem. They come out very naturally. Okay, so I take now a few more questions. One was, can we get a recording for the lecture? Yes, I record the lecture and will share it with you. Then another one, if the Laplacian matrix part you mentioned, in the Laplacian matrix part, is the Laplacian matrix is used to find if the network graph is connected. Why is it important to know if the graph is connected for federated learning? Good question. So it might be useful to know if you get information from a specific type of device. So let's say you would like to know in your federated learning system, is there anybody included from Austria? Because you would like to have this different perspective from Austria, for example. The next question, are physical limitations of devices taken into account in a federated learning network? Do you scale the model based on the respective devices somehow? Very good question. So in principle, you can choose this federated learning network. You can write it down on paper as you wish. But that's just a model, as I said. And the question is, how useful is the model? So if you in your federated learning network, you have here a node where the where the model is a 100 billion parameter deep neural network, then it might not be a useful mathematical abstraction for a system where this node is actually a small Raspberry Pi computer. So you should take into account the computational abilities of the nodes when you choose these local models. But so in other words, these local models that you write down here in the federated learning network abstraction should reflect the actual models that you train here, because I guess you will not train a 100 billion parameter transformer network in a Raspberry Pi. Next question. In the example with the 3 IP devices, only Y hat is exchanged. Is the X used so the features used to generate predictions the same for all devices? Doesn't it violate privacy? How would the augmentation work? Very good point. So as I mentioned, we leave it open in this course to some extent how this test set or this augmentation works in practice. So you can agree on a test set between any two participants. So let's say this device and this device define each other and agree on a test set which is purely randomly generated. So there is no privacy loss there. But of course, when you then use the predictions of this model on the test set and share it with the other device, you will have some privacy leakage. And then you then have to study how much privacy leakage is there. So we will see later how to quantify this privacy leakage. But there will be some privacy leakage, yes. Next question, how to deal with degraded performance by one of few nodes. Would it have negative impact on other nodes? Very good point. Yes, in general, the more nodes are active and running quick, the better. So how much will it hurt if, for example, in this federated learning system, this device here falls flat? And we will see then in the lecture next week asynchronous algorithms. So these federated learning algorithms that I will show you, they are tolerant to some extent, but they will slow down. So the more devices drop out, the slower the training will become, but it will not break down completely. There will always be a bit of progress as long as there are sufficiently many networks connected, sufficiently many devices connected. But when some of the nodes slow down or fall flat completely, the training progress will slow down. Okay, next question. The first example of federated learning, I need to confirm, is there a base node like the node with IP address 02? No, just in this example, I choose that this device doesn't collaborate. But so it collaborates. It collaborates by sending its predictions to this device, but it doesn't use the predictions of others. So it's a very generous device. It shares its predictions, but it doesn't try to leverage the predictions of others. That was just a random example. Yes, then Eckhart, there are questions from the lecture hall. Can you please relay them?